Hello friends, today's question. Two pulses in a stretched string whose centers are initially 8 cm apart are moving towards each other as shown in figure. Speed of each pulse is 2 cm per second. After 2 seconds, the total energy of the pulse will be. So they have two pulses. Let us call this the first pulse and the second pulse moving towards each other. Initially, the distance between them, centers of them is 8 cm. We have to find out what will the energy of the pulse after 2 seconds. So before we calculate energy of the pulses rather, we have to find out what will be the position of each pulse after 2 seconds. Okay, from that we can easily calculate what will be the total energy that will be associated with pulse 1 as well as pulse 2. So we have given, let us write initial setup. Or we can see initial position. So in initial position, the two pulses are 8 cm apart. And each pulse is moving with the speed of 2 cm per second. Each pulse is traveling at speed which is 2 cm per second. Now let us calculate their final position, which we have to find out that after 2 seconds. Final position of pulses so you can see after you can see in 2 seconds each pulse will be traveling a distance, let us suppose that is d, and d will be equal to speed multiplied by time. Speed is given as 2 cm, time is our 2. Okay, so you can say that distance will be 4 cm. So you can say in 2 seconds each pulse will travel a distance of d, which is equal to speed multiplied by time. So this will be 2 multiplied by 2, which comes as 4 cm. So the distance traveled by one pulse is 4 cm. So total distance traveled by each pulse, or we can total distance traveled by both pulses, total distance traveled by both pulse will be equal to distance of one pulse plus distance of second pulse, which will be 4 plus 4 and is equal to 8 cm. So distance traveled by pulses is 4 plus 4. So it means both pulses will travel a equal distance of 4 cm toward each other, and at one point they are going to merge. It means after 2 seconds the both pulses, pulse number 1 as well as pulse number 2, are going to superimpose each other. From here we can say as the distance traveled is equal to the initial separation of the pulses therefore the pulses will superpose each other. Therefore, the pulses will superimpose. Okay. And you can see that pulse number 1 is having a crest on the upper side, pulse number 2 is having a crest on the downward side. So as they superimpose each other, these pulses will, this crest will cancel each other and a destructive interference will be formed. So we can say from here that since pulse 1 has upward crest and pulse 2 has downward crest, therefore the pulses will cancel each other at the moment of complete overlap. At the moment of complete overlap due to destructive interference. Due to destructive interference. So which basically means that initially the pulse is 1 is like this, 2 is like this is pulse number 1 and 2 moving towards each other, and later on it will be becoming something like this. Suppose they meet at this point P, so this will be a point P, which will be nothing but a flat, you can say, having zero amplitude. Now we are interested in finding out what will be the total energy of the pulses. Okay. So let us say energy of the system. So if you look on the figure itself, we get a little confused because here the pulses 1 number and pulse number 2 are having some kind of energy associated with it, but when they go through destructive interference from the figure, it looks like that the entire energy is lost or it becomes zero. But if entire energy is lost, then the principle of total energy conservation is going to fail, which is not going to happen. Okay, so we can say energy of the system, total mechanical energy is conserved. So we have to remember this principle, that total mechanical energy is conserved. So if the energy is conserved, we can say that even though the pulses temporarily cancels in amplitude during overlap, but energy do not vanish. So we keep in this principle in mind. So from here we can draw one important conclusion, that while the pulses temporarily cancel in amplitude during overlap, but energy does not vanish. So it means the energy now is temporarily stored as a kinetic energy of the string particle instead of the potential energy in form of the displacement. So now the entire energy is stored in the form of a, you can say, kinetic energy. So you can say from here, it is temporarily stored as kinetic energy of the string particle instead of being in the form of potential energy due to displacement. So therefore, here we can say the entire energy will be purely kinetic. We can say energy is purely kinetic. So option number B is the correct option. Option B is correct. And we can also find out the energy also. What will be this energy? So let us write the formula for energy of a single pulse. We have two pulses. Energy of pulse number 1. So you can say energy of pulse 1, that is called that E1, that will be equal to half mu v square a square, and here mu is our linear mass density. Linear mass density. V is the velocity and A is the amplitude. So as both the pulses look same with the same amplitude and same velocity, so we can say total energy, let us suppose that is E, will be equal to twice of E1, and that becomes twice into half mu v square a square. Half and half goes away, so the energy comes as mu a square v square. And at overlap, we just concluded that the energy will be purely kinetic. So we can say at overlap, total energy, which was E, will be equal to our kinetic energy. Therefore, we can say the kinetic energy will be equal to mu A square V square. So in this way, we can also find out what will be the amount of kinetic energy. So this completes the question. Thank you.